concept of an outlier or outliers. Now, outliers is a statistical idea that most people think they understand, but what they think they know is wrong. And that's called a misconception. And misconceptions are the most dangerous things in learning or in instruction. Because when you think you know it, you don't ask about it, or even if somebody's trying to tell you about it, you don't pay attention because you think you know it, right? Okay. But if I went over to Harrington and in an unlikely but possible temporary psychotic break started shooting people, and I shot all the people on the faculty who thought they knew what an outlier was but knew it wrong, there'd be a lot of job openings. People think outliers are people who are just so weird that they ought to be branded on their back with a giant scarlet O, or tattooed on their forehead with a giant scarlet O. It is true that outliers are weird. But what we need to understand about outliers is everybody's weird on some variables. Everybody's really good on some things and really bad on other things, right? We're all outliers on some variables. And it's true, some people are outliers on a lot of variables, and some people are outliers on relatively few, but we are all outliers. We have all sinned and need forgiveness. It's also important for you to reflect on the fact that I'm about to say, which is in a given data set, a person may be an outlier on some statistics for that data set, but not on other statistics for the data set. So it can be, maybe you're an outlier on variable X, or maybe you're an outlier on variable Y. Maybe you're an outlier on the mean of X, but maybe not some other statistic that for X. Now, a problem that we have in statistics is that the statistics that we typically compute, that we're going to learn about this semester and next semester, most of, not all, but most of what we'll be learning about, the statistics are heavily influenced by the outliers. The outliers will exert a disproportionate influence on our answers, disproportionate to their numbers, and could distort the answers that we get. The statistics that we're learning about were not on the clay tablets that Moses brought down from the mountain. They were invented by people, and most of them were invented by people relatively recently. You know, the mean is old, the median is a lot newer. Some of the other statistics we'll learn about are a lot newer. For example, the Pearson correlation coefficient was invented by Carl Pearson in the late 1800s. We're going to be learning about the t-test. That was invented by a Dublin Guinness brewery worker named Gossett. We'll talk more about that. In 1908, ANOVA we'll be learning about was mainly invented primarily by Ronald Fisher in the mid-20s. So all these things are relatively new. They are all heavily influenced by outliers, and so you have to worry about outliers. And because everybody's an outlier on some variables, the implication is that it will be rare that you don't have outliers in your data. the implication is that it will be rare that you don't have outliers in your data. And because they can distort the hell out of your answers, you need to worry about whether you have outliers. You can look at your data and see, here's somebody whose scores are way weird, and maybe they're an outlier, at least as regards some statistics. The question is, what do you do about it? And there's no way to definitively decide whether somebody is an outlier for sure and whether they ought to be deleted from the data set or not. There are statistical ways to quantify how weird people are, but that doesn't help ultimately make the decision what to do with people. I don't like personally to delete outliers from data unless I can figure out why they're outliers. You know, sometimes you can look at the files, the academic records of the people in the study, or you can actually do something real bizarre called go talk to the damn people. You know? Like, hey Joe, your scores were kind of unusual. Were you feeling bad that day? Did you have a temporary psychotic episode? Did you do some crystal meth before you took the test? And, you know, if they say, you know, I was sick or I was psychotic or I was, you know, whatever, then I think you ought to delete them from the data. I'll give you an example of this. When I was a high school teacher, we gave standardized tests at the end of the school year. Iowa Test of Basic Skills. I was walking up and down the aisles while they were doing it. This one kid's answer sheet, he was going quite rapidly through the questions, filling in his answer sheet. It struck me as somewhat unusual to see his answer sheet. The bubbles that he had colored in made a shape that was a perfect Christmas tree. And it occurred to me he was not actually reading the questions and was just making a Christmas tree design on the answer sheet. Perhaps he was an outlier and needed to be deleted from the data if I was doing this study. Everybody got the basic idea? Okay. Now, all the statistics we're going to learn about are old. People have long been worried, not all of them, but a lot of what they learn about are old. People have been worried about outliers and the fact that they can distort your answers a lot for a long time. And more recently, people have focused on developing alternative ways to characterize data than the traditional ways that we're going to emphasize. And these are called robust statistics. And examples are in the location statistics. The trim mean and the Winsorized mean are robust location statistics. And you can read in the book what those are. Some of them are actually old also. For example, the Winsorized mean was invented by a British minister named Charles Windsor hundreds of years ago. But the commonly used statistics that we're going to learn about mostly are not robust, which means if you're going to use them, if you're going to use the mean and you're going to use the median, for example, you need to worry about, do your data have a lot of outliers or not? If your data do have a lot of outliers, you may need to make a decision to get rid of them, or you may need to make a decision to compute a robust statistic instead of the more traditional statistics. There was an article written recently in the American Psychologist by a famous statistician. It was titled something like how many discoveries have we failed to make because we do not use robust statistics? And it's a very good article, and it argues that we ought to not do all the traditional stuff. We ought to start using the robust statistical stuff. And the book has some examples of robust statistics. For example, the Winsorized mean and the trim mean. But most of what we're going to be learning about are statistics that are not robust statistics. Okay. Now, one of the 18 or 19 of you presenting at SERA has the topic robust statistics, I believe. Who is that? That guy right there is going to be writing a paper on robust statistics. And we'll learn a lot more about it, and you might want to get him to talk to you later about robust statistics if you're really interested in robust statistics. Okay? Is that the basic idea of robust statistics? Okay. Now, somebody asked me about iteration, right? You want me to talk a little about iteration? In the rectangular object containing knowledge, in the chapter on location statistics, there's discussion of location statistics developed by a statistician named Huber, which is called the Huber estimator. A key preliminary idea is that in statistics there are two ways to get statistical answers or statistical characterizations. One way is you have a statistic that you solve for by using a formula. So far that's been true of everything we've talked about. We've talked about the mode and the median and the mean, and formulas or algorithms are used to solve for those three things. There is a second way in statistics to find an answer, to solve for an estimate, even if there is not a formula. It is a statistical process called iteration. What you do if you don't have a formula, if you know the properties that the answer ought to have, you can make an initial guess as to what the answer may be, and then keep tweaking the guess until you get a number that has the expected properties. Almost always this is done with a computer program because this is very computationally difficult to keep tweaking the answer until you get an answer that has the desired properties. The Huber estimator, discussed in the rectangular object containing knowledge, yields a location statistic, and we solve for that location statistic not with a formula but with this computer-intensive method called iteration. You know, sometimes, like I go to APA. I just was there a few weeks ago in Boston, and I was lecturing doing training sessions. I usually do 3 training sessions at APA. And we had to do some iteration. And believe me, a lot of people at APA, they're not statistical whizzes, they're therapists who are wanting maybe to learn a little more about statistics. They left that session where we iterated as changed people. Because after you've iterated the first time, you're just a different person. And you always remember the first time that you iterated vividly. So I remember where I was and what happened. And you always remember it. It's a special moment. Now, I'm not going to say a lot more about iteration. SPSS will iterate. It will, for example, give you the Huber estimator. So that's the basic idea of iteration. If you want to know a little bit more about iteration, you could do a wiki search on iteration and probably get a fairly accessible, non-technical explanation in Wikipedia about what iteration is. Okay? All right.
In chapter 1, there was a chunk of information about normative versus dictative measurements.
Ipsative
measurements.
Right.
Are those like the same? Can you do the same mean, median, mode type calculations with those kinds of measurements, or I just didn't know what that chunk of information?
Well, typically, there is a level of scale issue involved in whether you have ipsative or normative measurement. Essentially, a normative measurement is where your answer to one question has no effect or imposes no constraint, mechanical constraint, on your answer to the other questions. For example, if the first question is, Bruce is extremely attractive, and then there's a Likert scale. And the second question is, I don't know, Bruce is a chick magnet, Likert scale. There's no mechanical constraint that would require your answers to the first question to impact your answer to the second question. Logically, probably, if you gave me a 4 on the first one, you'd probably give me a 3 or a 4 on the second one, right? But mechanically, there would be no constraint from giving me a 4 on the first one and a 1 on the second one. In an ipsative measurement, there are mechanical constraints that each answer impacts the remaining things that you can do. For example, there's an instrument called the Rokeach Values Survey. And it has 2 parts. And the first part lists 18 values. Like, I don't remember exactly what they are. They're things like wisdom, knowledge, honesty, things like that. And what you do on the instrument, you say, the most important one is this one, and I give it a 1, and the second most important is this one, and I give it a 2, etc., right? You have to rank order the values in terms of how important they are to you with no ties. And that means that's ipsative, because once you put wisdom number is the most important thing, then you can't put any of the others as the most important. Or another example might be, a lot of times when you're going to invest, in order to protect their butts legally, brokerage houses will make you talk about what your investment objectives are. And they'll say, how important is it to protect your initial investment, the principal? How important is it to generate an income stream off the investment? And how important is it to have growth in the principal? Okay? And a lot of times they'll do things like they'll say, allocate exactly 100 points to these 3 things, such that the total of these three things is exactly 100 points. And that's an ipsative measurement also. Okay? Now, why do we do ipsative measurements? Well, normally we might prefer normative, but for some situations, we wouldn't get a variable even if we did normative measurement. Like on the values thing. If you have people rate on a 1 to 4 scale how important honesty was, how important wisdom is, how important beauty is, etc., except for a few whack job people, you'd get every item rated a 4. Really important stuff, right? If if you want to get any variability in the data, you're going to have to go to an ipsative measurement. There's another reason that sometimes we use ipsative measurement. In the real world, we can't pursue every value. We have to make choices. It's fine to say, I value honesty, I value wisdom, I value beauty, I value knowledge, etc. But in the real world, where the day only has so many minutes, etc., you can't spend your time trying to achieve all 18 of those damn things. In the real world, you have to make choices and say, this is the most important thing to me, and this is second most important. And so in this example, ipsative measurement honors the reality of how you operate within the domain of that construct. And so ipsative measurement might be desirable in that example. There is a level of scale implication. Obviously, if you had people do the Likert scale rating of the human values, the data would be arguably, at least possibly, interval. If you have people do the rank ordering thing, definitely not interval. Ordinal data, right? Okay. Does that help you with the ipsative normative thing? Okay. All right. Any other questions?
Can you explain a little bit the difference between mediator and moderator?
Let's find a statement in the book that says the primary difference. Show me a page number that says the main difference between those two things.
9.
Page 9. Can I borrow your book for a second? Okay. In several places in the book, and you might want to use the index to find all, and I think you would be successful. Look in the index under both terms and find everywhere in the book that the two terms are defined. Okay. But on page 11, it says, moderators tell you about when or for whom relationships operate. Mediators help you understand how or why relationships occur. And I think that's the essential thing. There are examples in the book of mediators and moderators. I'll give you an example of a moderator. I do come by periodically during the semester just to see if you're highlighting. Okay? And I like you to use multiple colors, and I like lots of stuff highlighted. So you don't have to read the damn book, but you need to highlight a lot. Okay? Moderator tells you about when or for whom relationships occur. An example would be, there's a famous study done in medicine about the effect of taking an aspirin on whether you have a heart attack. Okay? A lot of medical studies actually are done with either nurses or doctors. And the reason is because in medical interventions, including medical research, a big problem is the damn patients don't take the damn medicine. You know, classically, a lot of people, if they have an infection, a sore throat or whatever, the doctor gives them 12 days of penicillin or whatever it might be and says, take this for 12 days. And very commonly, people take it for 6 days. They no longer have a fever, and they decide to stop taking it. Maybe they also decide to stop taking it, so they got 6 penicillin tablets left for the next time they're sick. They don't have to pay the money. They don't have to go to the doctor. They can self-medicate, right? Or blood pressure medicine. A lot of people have blood pressure prescriptions. Relatively few of them take it every day. They take it, they feel better, they stop taking it. Of course, the really big example of non-compliance is in psychotropic medications, like for schizophrenia. And it's classic. Schizophrenics, they take their medicine, they feel better, they are better, they stop taking the medicine because they feel better, and guess what happens? They get psychotic again, right? Okay, so a lot of studies in medicine are done with doctors and physicians because the premise is you don't take the damn medicine that you're trying to find out whether it works or doesn't work. The major study was done a few years ago with 25,000 physicians as the participants. Half of them randomly took an aspirin every day. Half of them took a placebo every day. And, of course, they didn't know what they were taking. In medical research, you always have a plan as to how long you're going to do this study. We're going to do it for a year or 2 years or whatever. However, in medical research, it's possible that during the study, before the planned time period has elapsed, that you will achieve a definitive result even though you haven't gone the full planned amount of time. And when that happens, ethically you must immediately stop the study and make available the treatment to everyone, or at least announce the results to everyone. And this study was stopped because they found out that if you take an aspirin every day, you're half as likely to have a heart attack than if you don't take an aspirin every day. Seemed to be an important finding. Heart attacks are real bad things. And aspirin is damn cheap. It doesn't seem to have a lot of bad side effects. It even may have other benefits. Like it's possible, it's not sure yet, but it's possible aspirin also reduces your risk of colon polyps and colon cancer. Okay? So, all right, here's an example of a study. Now, I believe that study was only done on men. Okay? Of course, the reason is in physiology, men and women are different. I can explain it to you, but we don't have time. All right? And, in some things, men and different aren't that different. But in some things, they're just hugely different. To be on the safe side, often in drug research, you use only all men or only all women. Okay? Now, what if we repeat the study of aspirin with only women, which, by the way, has been done? And the effect of aspirin, it's not as conclusive, I don't believe, yet, but the effect of aspirin on heart attack is not as positive for women. That means gender is a moderator for the effect of aspirin on heart attack. Now, a mediator is a variable that either accounts for or helps you understand the mechanism by which something works. In the aspirin example, there are a couple of potential mechanisms by which aspirin reduces heart attack. The main explanation appears to be that a heart attack is the formation of a blood clot that blocks flow of arterial blood to the heart. And the mechanism of that clot forming is related to inflammation of the blood vessels. And we believe that aspirin, we know that aspirin reduces inflammation. And we also, aspirin is an anticoagulant and reduces the formation of clots, because clots are clotted blood inside a vein or an artery. So, if I did a study where I either did or didn't give people aspirin, and I measured how there are measurements that you can do of blood to figure out how prone to clotting it is. Okay, there are tests that you can do for that. And maybe there would be a measurement that could be made of inflammation in the blood vessels near the heart. I don't know that that's possible, but let's say that was possible. And then we measure heart attack. Now we've got 4 variables rather than 2. And our study, we would look at, does the aspirin affect the tendency of blood to clot? Does the aspirin affect inflammation of the blood vessels? And how do those 2 things affect whether you have a heart attack or not? That would be an example of mediation kind of stuff. Okay? The moderator and mediator kind of stuff is really important. And lately in scientific psychology and education research, we more and more are paying attention to these things. It's a more nuanced understanding for whom or why things work or don't work. Okay? Other questions? From the rectangular object containing knowledge or other things? Okay. I want to talk for a while about the second class of statistics. Having talked about location or central tendency, let's talk about the second of the 4 classes of statistics, which measure dispersion or spread outness. We can think of these statistics as answering the question, how dissimilar are the scores to each other? Now, if you think about that question, the question itself implies that all the statistics that measure dispersion must be at least intervally scaled. Because you can't talk reasonably about how far apart the scores are unless the ruler they were measured on has got equal units on it. By the way, I need to say one thing about interval measurement and that ruler. The critical thing is not that the people's data that you have a person at each interval. The critical thing is the ruler itself has got equally spaced marks on it. Everybody follow that? We can't talk about how similar or dissimilar the scores are if we haven't got interval data, because then we can't measure the distances of the scores from each other unless we have interval data. Everybody follow that? Okay. Now, if you think about what we're asking with dispersion statistics, you will also realize another property of all dispersion statistics. What is the least dissimilar that scores can be from each other in a data set? What? when the scores are all the same or a constant, right? Okay. In other words, the least dissimilar the scores in a data set can be is zero dissimilar, which would happen when all the scores are the same in a data set, right? Everybody follow that? The implication of that realization is that dispersion statistics can never be less than zero. You can't have scores that are even less dissimilar than being identical. A negative dispersion statistic, like if your answer was -5 for dispersion, that would say the scores are even more similar than they would be if they were identical. That does not make any sense. Does everybody follow that? So logically, you can never have any dispersion statistic that is less than zero. Now let me give you, an example of some of the things I do on the exams to make you think. Remember I told you before that in statistics you can usually get an answer to a puzzlement or a question either intuitively, conceptually, graphically, or mathematically, right? I'll give you some examples of what I will do to test your understanding of dispersion. I'll show you some data, and I'll ask about what is, and I'll name a statistic that measures dispersion for the following data. And I'll have a set of answers like this. A, -53.2. B, -20.5. C, -1. Or D, 2.3. And those will be the only answers. And if you know the formula for the dispersion statistic I'm asking about, you can sit there during the exam and use the calculator I'm allowing you to bring and compute that the answer is 2.3. In the alternative, you can think of what we just talked about and say there's only one positive number, dispersion can't be negative, the answer has got to be D. Okay? But I also want to emphasize that when you leave the exams, you know those electrical devices that kills flies and stuff? I got me 2 big ones that are human size that I mount on the 2 doors. And anybody that chooses A, B, or C to that kind of question, you're going to know it when they leave the room because you're going to hear and you're going to hear screaming. Okay? All right. Now, another thing I might do on the exam is I might give you 15 pages of scores, each of which are 25 digits in size. In other words, they will not fit in a calculator, a regular calculator. Or I might give you 25 pages of 3-digit numbers and ask you about the dispersion of these data. If I do the last thing, the people who are calculator mathematical people will spend 3 hours computing the dispersion statistic for the data. They will get the correct answer. Regrettably, that will be the only question they will have time to answer. And they will only have one correct answer on the exam. Okay? So these are some of the kind of things that we can do on the exam. All right? Everybody got the basic idea about dispersion? Okay. Now, another key critical statistical concept is the concept that statistics are in one of two general worlds. And for every statistic, you need to know what world the statistic is in. One world is called the score world, and things in the score world are in an unsquared metric. And the other world is called the area world, and everything in the area world is in a squared metric. Some of the things in the area world explicitly let you know they're in the area world because they may have a superscript of 2 on them. Or some of the things in the area world, the name may tell you that in the area world, like the sum of squares. Guess what world the sum of squares is in? It's in the area world, right? Okay. Now we also can subdivide the score world into 2 subparts. One part is called the unstandardized score world. And everything in the unstandardized score world is in the metric of the original scores. Okay? And everything in the other subpart is called the standardized score world. And what that means is you have removed from those statistics the standard deviation by dividing the answer by the standard deviation. Okay? Okay. Now, I want to go back. The key idea, the take-home message for every statistic we learn about, you need to know what world the statistic is in. Did I say you need to know odd numbers nights? Or only between the hours of 5 and 6? No. Did I say you need to know for some statistics what world they're in? No. I said you need to know for all statistics what world they're in. Okay? This is fundamentally important to know that. Now let's talk more about this for a minute. I'll mention that some dispersion statistics are in the score world and some are in the area world. But I want to go back and talk for a minute about, for example, the location statistics. The location statistics are in the unstandardized score world. The statistics are in the same metric as the original scores. Now let me explain this in a little more detail. First, I have to give you a little background of the law. Some of you were not raised in Texas and do not know Texas law, especially the students who are international students do not know Texas law. I need to understand some unique features of Texas law, particularly if you've just moved here a few weeks ago. In Texas, in any state, it is legal for you to use lethal force to protect yourself against an imminent threat to your safety, your health, or whether you might be even in danger of dying. It's legal to protect yourself to kill the other person with lethal force. Is that clear? That's not new. That's pretty much true everywhere in the world. But in Texas, it's legal to use lethal force to protect your property if it is dark, if it's nighttime. For example, I guess it was about 8 or 9 years ago, there's a guy in Houston, had a pickup truck. He lost his job and quit making payments. The repo guy came out to his house to the carport at 3 a.m. and hot-wired his car and started driving off in it. And the guy heard it. And he took a deer rifle out in the front yard and he made a headshot from 3 blocks and killed the repo guy. And the police came. And they said, that wasn't very nice. That was not very neighborly. That's not very Texan to do that. But they did not arrest his ass because that's perfectly legal. Okay? This is why, a lot of you probably go out drinking after class. You go over to the Fox and Hound or somewhere else and drink, or Connie's or whatever. In Texas, at every bar in Texas, when the news comes on, everybody's watching the weather. That's not so they can see where Hannah is or Faye or Ike or whatever. That's so they can know tonight what time does night begin and when it ends. It's really important to know that in Texas. Okay. Now, there's a slightly not as widely known part of Texas law that means professors, under certain circumstances, even when they're not needing to protect themselves from imminent danger, can shoot students. And I'm going to give you an example of when you're allowed as a professor to shoot a student. If I say that there are scores of 3 people and they have respectively $1, $2, and $3, and I ask you what the mean is, and I've already told you the mean is in the unstandardized score world in the same metric as the scores, right? Okay. If you say 2, I'm probably going to shoot you. Because that's not correct. The correct answer is the mean is $2. Does everybody understand that? Okay. For any statistic that's in the unstandardized score world, you need to say that metric as part of the answer. Okay? Or haven't covered it yet, but there's a dispersion statistic called the range, and there's a dispersion statistic called the standard deviation. They are both in the unstandardized score world. If we have people with data $1, $2, $3, and I ask you what the standard deviation is, don't tell me if the correct number is 0.66. Don't tell me 0.66 is the standard deviation. Tell me it's $0.66 or 66 cents or 2/3 of a dollar. Any of those answers are good and they don't skip your shot. Okay? So this is really important for you to remember for every statistic what world the statistic is in, and for statistics in the unstandardized score world, to say that metric when you give the answer. Is everybody clear on this? Okay? I really don't want to shoot any of you. I am allowed to. I will if I have to. We do admit a few extra students into 640 so that if we have some what's called in experimental design called mortality, the class can still go on. And doctoral students are smart, and sometimes if you shoot 1 or 2 of them, the rest of them pick up on the key points. But I really would rather not have to shoot any of you. So please remember this idea of the worlds of statistics, and for everything we learn, know clearly and unambiguously what world it's in. Okay? All right. We'll go ahead and stop. Everybody's clear who's writing practice questions for next week? Okay.